Hello everybody, today I'm going to explain and demonstrate what are stationary waves. Alright, let's get started. So a stationary wave, also known as a standing wave, is a combination of two waves having equal amplitude and frequency, but they move in opposite directions. Now stationary waves are formed due to interference between two waves. Now it's a combination of constructive and destructive interference that leads to the stationary wave pattern. Now why is it called stationary wave or standing wave? That's because the observed wave pattern is characterized by points that appears to be standing still. So it appears standing still, hence the name. Actually, it moves back and forth very quickly, but then as it appears to be still, it's called stationary or standing wave. Now, most important point is stationary waves can be created only when their motion is restricted to a finite region. So they should be bound. There should be a boundary for those waves. So the waves cannot travel infinitely long. Why is a boundary required? So that the waves reflect and then they interfere with the incoming waves and create the stationary wave pattern. So this is how a stationary wave looks like. Now I've used different colors for the purpose of representation. In fact, there is only one wave, the black wave. As it travels from left to right, it's meeting a boundary, and then it's going to reflect, change in phase, and then become the red wave, and then travel from right to left, and then the process goes on and you get the stationary wave. We'll look at how the stationary wave is even formed later in this video. So this is the stationary wave equation, 2a into cosine of 2 pi x by lambda and sine of 2 pi t by the time period. One most important thing is, although we say stationary wave, it's not actually a wave. It doesn't travel backward and forward. Rather, it's a pattern resulting from the presence of two waves which have same amplitude, same frequency, but the only difference is they move in opposite directions, which creates the stationary wave pattern. Alright, let's understand some basics of wave. So what is a wave? It's an oscillation, It resembles a sinusoidal curve. It is a sine function. So if you look here, the wave starts at 0, reaches a positive extrema, and then comes back to 0, goes to a negative extrema, and then comes back to a point which is in phase with where it started. So the maximum displacement of the wave is called the amplitude. There are two maximum displacements. One is the positive amplitude and one is near the negative amplitude. Then you have two regions called crest and trough. The one above toward the positive extrema is called the crest. The one below toward the negative extrema is called the trough. And the time that it takes for the wave to complete one single oscillation, meaning one crest and one trough, is the time period. And wavelength is also the distance of one crest and one trough. And a more advanced definition of wavelength would be the distance between 2 points that are in phase. That's what I've shown here. Alright, now how is a stationary wave even formed? Well, let's consider a wave traveling along the x-axis from left to right. Now, for stationary waves, you need to have boundaries so that they can undergo reflection. So there is a boundary on the right end, and the wave travels from left to right. It hits the boundary, undergoes reflection and a change in phase. Now the reflected wave travels along the x-axis until it reaches the other fixation on the left side. But while it is traveling along the x-axis, there might be another wave coming from the left to right, and that's where the interference can take place. It can be constructive or destructive interference, which will lead to the formation of stationary waves. So the fixed ends are called the nodes or points of zero displacement, and the free ends or antinodes or points of maximum displacement. Now don't worry about nodes and antinodes. We'll be looking at the diagrams soon. So let's consider a wave. Okay, it's traveling from left to right. It's in black color, and when the wave undergoes reflection, I'll change the color to red so that you can have a visual representation of what's going on. So now this black wave is going to travel from left to right, and we will increment the traveling distance by 90 degrees or pi by 2 radian. So now the black wave has traveled 90 degrees and then it has undergone a reflection, and now the reflected wave, which is a red wave, has not only changed its direction, but also it has changed its phase. Now the red wave is moving forward, is moving toward left, whereas the black wave is moving right. And now at this point we can see that the red wave is overlapping the black wave, which means it is it is interfering constructively. Now again, the black wave is moved pi by 2 radian toward the right, the red wave is moved pi by 2 radian toward the left. Now we can see that the waves are canceling each other, meaning they're undergoing destructive interference. Again, there is a phase shift and the waves are interfering constructively. Well, now the waves are interfering destructively. Again, constructive interference, destructive interference. So as you can see, the process keeps repeating. Constructive and destructive interference are following each other. Again, constructive interference, and finally destructive interference. So this process will keep going on. We can go further. We can keep pushing the black wave toward the right, the red wave toward the left, and you will get this alternating pattern of constructive and destructive interference, which results in the formation of nodes and antinodes, and which also results in a stationary wave formation. Now, when the amplitude and frequency are constant, it'll result in a beautiful constructive and destructive interference pattern. But what if the signal is a complex combination of different frequencies and different amplitudes? Like this. It's a complex waveform. It's a complex combination of different frequencies and different amplitudes, representing the real-life scenario. So in this example, as you can observe, there is a waveform toward the right, which is largest among the three, and it has a large wavelength, which means it's a low-frequency waveform. And as you move toward the right, you can see that the wavelength is decreasing, and which means it's a high-frequency waveform. Not only that, the amplitude is also decreasing. So this is a complex combination, and do you think it'll result in a stationary wave pattern, assuming that we have put boundaries on both ends? Well, no, it'll not, because the phase relationship between the reflected wave and this wave will not be classified as either constructive interference or destructive interference. It's just going to be a random interference which will result in a random waveform. But let's have a look at it anyway. Now let's say the black wave moves 90 degrees toward the right. So right now the black wave is moved 90 degrees and it undergoes reflection and a phase change, and that's where the red wave comes in. So right now we can observe that the red wave and the black wave are out of phase. So they're undergoing destructive interference. Now the black wave moves a further 90 degrees, the red wave moves a further 90 degrees toward the left, and we can observe that the red wave and the black wave are overlapping, meaning they're undergoing constructive interference. So far so good. But right now, again, they have traversed another 90 degrees, but there is no definite phase relationship between the black wave and the red wave. We can't say for sure if it's a constructive or destructive interference. It's just a random interference which will result in a random waveform. And this is what's going to happen as we move forward. As you can see here, we can't really say if it's a constructive or destructive interference. Again, a further 90-degree travel. Even here, maybe here we can say toward the right there is a constructive interference, but then later we don't know if it's a constructive or destructive. And so on and so forth. So this doesn't result in a stationary wave pattern. You need a waveform that has same frequency and amplitude so that the reflected wave also interacts with the incoming wave such a way that it results in a predictable constructive interference and destructive interference, which leads to a stationary wave pattern. Alright, let's talk about nodes and antinodes. So each standing wave pattern or stationary wave pattern has both nodes and antinodes. Nodes are the points where there is no displacement at all. So they appear to be standing still because there is no displacement. And why are nodes even formed? Because they're formed as a result of destructive interference between two waves. On the contrary, there are certain points that have maximum displacement, that is positive and negative displacement, in each vibration cycle. So those points are called antinodes. Now, antinodes are the result of constructive interference between the two waves. So as we know that a standing wave has both constructive and destructive interference, which results in the formation of nodes and antinodes. So let's look at a pictorial representation of nodes and antinodes in a standing wave pattern. So the regions marked yellow are the nodes, and the regions marked green are the antinodes. As you can observe, the regions marked yellow, they're just appearing to be present there. There is no displacement at all. Whereas the regions marked green are going up and down. So up meaning positive displacement, down meaning negative displacement. So it's just a direction. At the end of the day, the magnitude is still the same. So another note about nodes and antinodes. Distance between two consecutive nodes is lambda over 2. So lambda is the wavelength of the wave. Distance between two consecutive antinodes is also the same, lambda by 2. But distance between a node and an adjacent antinode is lambda by 4. Let's look at the wave. So here, distance between two nodes, so distance between two yellow points, it is lambda by 2, right? So as you know, the wave is one crest, one wavelength is one crest and one trough. And the distance between two yellow dots is just either one crest or one trough, depending where you look at. It's just lambda over 2. And the same way, the distance between two green points is also lambda over 2 if you calculate it. Whereas the distance between yellow point and green point is lambda over 4 because it is just half of the distance between two yellow points. So that's what I've mentioned here. All right. Now, what is a traveling wave? Now, why I've included the topic of traveling wave here? It's because I want to tell you what is not a stationary wave. Well, a traveling wave is not a stationary wave. So traveling waves are observed when there is, when the wave is not confined to any boundary. So if there is no boundary, it means there is no reflection. If there is no reflection, it means that the wave is going to keep traveling on, and it's going to travel infinitely long. It'll never undergo any reflection. So how do you distinguish between traveling wave and stationary wave? Well, one way of distinguishing is that, we know that a traveling wave doesn't have any boundaries, no reflections, and is just going to travel infinitely long, whereas a stationary wave has a boundary, undergoes reflection. But is there any mathematical way of distinguishing between the two? Well, there is. It is called the standing wave ratio. Well, SWR is the ratio of the amplitude at the antinode to the amplitude at the node. So you know what are antinodes and nodes. So a standing wave has infinite SWR. Why is that? Because we know that the antinodes are the regions of maximum displacement, so it's going to be some maximum value. But the amplitude of the node is 0, right? The nodes are stationary. They're not even moving back and forth. So we know that 1 over 0 is not defined or infinity. So meaning if we can calculate this ratio, we know for sure it is a standing wave. And a standing wave also has a constant phase at any point, but only undergoes a 180-degree phase change at every reflection. Now the second example is a finite non-zero SWR. So this happens when the amplitude of the antinode is a maximum, whereas the amplitude of the node is not 0, but it's minimal compared to the amplitude of the antinode. And the wave is called a partially stationary wave or a partially traveling wave. And the final example is a standing wave ratio of 1, which indicates that the wave is a pure traveling wave. Thus, we can use standing wave ratio as a guide to distinguish between pure stationary, pure traveling, or partially stationary and partially traveling wave. Alright, so far we've been looking at standing waves along a string, which represents a one-dimensional system where the node is a point, which is 0 dimension. Now you can extend this concept to higher dimension. So standing waves along a plate or a membrane represents a two-dimensional system where the nodes are along a line, which is one dimension. And standing waves on a solid object represents a three-dimensional system where the nodes are along the surface, which is 2 dimensions. So this concept of standing waves along 2D and 3D objects are nothing but mode shapes. So they are a vast topic in themselves, and we'll definitely cover them in separate videos in the future. So now let's look at some mathematical relation between the length of the string and the wavelength of the wave. So they are given by this relation, L equals n over 2 times lambda, where L is the length of the string, lambda is the wavelength of the wave. Now n is an integer starting from 1 to infinity. So if n equals 1, it is the fundamental frequency or the first harmonic. N equals 2 represents the second harmonic or the first overtone. And n equals 3 represents the third harmonic or the second overtone, and this goes on and on. Now let's look at some standing wave patterns of first, second, third, and fourth harmonic. So this is a standing wave pattern of the first harmonic. So first harmonic meaning n equals 1. If you plug the n equals 1 in the equation, it becomes L equals 1 over 2 times lambda, or L is lambda over 2. Isn't it true? Because a wavelength is one crest and one trough, whereas in this case we can see either one crest or one trough depending on where you look, but definitely it's half of the wavelength. And also in this pattern, there are two nodes at either ends, and there is one antinode in the middle that is moving up and down, having maximum displacement. So this is the second harmonic. So n equals 2, we plug that in, we get L equals lambda. So wavelength is one crest and one trough, and that's exactly the length of L. And as we can observe here, there are three nodes, so two at the ends and one in the middle, and then two antinodes in between. The next is the third harmonic. So again, plug the value n equals 3 in the equation, you get 3 by 2 lambda. So you have, like 3 crests and 3 troughs. And again, you have like 4 nodes and 3 antinodes. And finally, you have the fourth harmonic, the same thing. You plug n equals 4 in the equation, and you have 2 wavelengths. So L equals 2 times lambda. All right. Now I have certain demos. So this is a stationary wave demo. So this is a first harmonic. So I'm going to be plucking a elastic band that I've stretched it. And I'm assuming like the boundary condition is 2 nodes on either end. And where I'm plucking is going to be the maximum displacement or the antinode. Watch it. Okay. I have another demo. So this I saw in a science exhibition. So this is a stationary wave illusion pattern. All right. Thank you for watching this video. I hope you understood and enjoyed it. Have a great day ahead.